Hello viewers, so in this video we are going to be proceeding with the second part of transition elements. So this video we are going to be starting individual chemistry of each and every element. This video is presented to you by Algembe, so if you advise subscribe to the channel and share the video to your friends so that you can all benefit as a group. Now looking at the chemistry of the individual transition elements, the first video we are looking at the physical properties as well as the chemical properties together with the electronic configurations that are involved by each or possessed by each of these elements. We also looked at the periodic trends which are very common under paper 1 of chemistry, and I hope that for you to transit to this video you've watched the introduction about transition chemistry video which was labeled as 001. So in this video, we are going to be covering the individual elements or the chemistry behind the individual elements up to chromium. So we're going to be starting with titanium as the first transition element, and we're going to go straight away to the reactions that are involving titanium. As I was comparing these notes, I made sure that I only bring examinable areas. So if at all your teacher gives you more than the notes I've given you, you should take this as your revision exercise because it only focuses at equipping you towards answering your examinations. So make sure that if you want detailed chemistry or detailed transition chemistry, maybe refer to the notes that your teacher will be giving you. This one is to equip you straight away to excel in your papers by focusing on the areas that are required. So we shall start with part A, involving reaction of titanium with air. Now when you're describing any reaction in inorganic chemistry, there must be conditions, and this is where majority of you make mistakes from. So for titanium to react with air, the first condition is that it must be heated. So that's why I say that heated titanium burns in oxygen to form titanium 4 oxide. Now each and every equation, as you're answering organic chemistry, you must present a statement first. Now in that statement, there must be conditions. For example here, we have heated titanium, that's the condition. And then later, there must be a product or the name of the product that is going to be formed in that equation. And we are going to be forming titanium 4 oxide. So that means that whenever we are heating titanium in air, it's going to burn in air to give us titanium 4 oxide. But before writing the equation, in case you're examined, you must first make sure that the condition and the product being formed are well stated in your statement that follows the equation. Each and every equation must carry a statement to maximize your marks. So going to the reaction number 2, we are going to look at the reaction with chlorine, and here it's the same condition. So heated titanium is going to burn in dry chlorine. So according to this one, the conditions are two. One of it is that titanium must be heated, and the other one is that chlorine must be dry. So that, and you must name the product that is being formed together in the same statement. So heated titanium burns in dry chlorine to give us titanium 4 chloride, and both of them are solids. So titanium reacting with chlorine gas to give us titanium 4 chloride. So make sure that this equation above here is balanced by putting here 2. Sorry, that one will be the way it is. Titanium oxide is TiO2 and titanium 4 chloride is TiCl4. So let's go to the third reaction, which is going to be involving reaction of titanium as an element with the acids. So we are going to look at titanium. Titanium is going to be oxidized by hot concentrated. Now the condition here on the acid is going to be hot concentrated. And for you to qualify a mark for the statement, you must represent all the conditions that are required whenever you are answering a specific question. The statement to the equation must contain all the conditions together with the products that are going to be formed. Well stated. So you're going to say that titanium is oxidized by hot concentrated sulfuric acid to titanium 4 sulfate. and the acid is reduced to sulfur dioxide together with water. And we say that such reactions are redox reactions, and we looked at the balancing of these further in details. We say that with redox reactions, you ionize sulfuric acid. That means that you are going to have sulfate ions. I'm just giving a highlight about or remembering you about balancing equations that involve oxidizing agents. We say that we use redox reaction knowledge. So if you ionize sulfuric acid, you're going to get sulfate ions together with protons. And we say that in redox reactions, the side which has protons is going to have electrons too. And we say that this acid is going to be reduced to sulfur dioxide together with water. So you balance this equation according to redox reaction knowledge, as it was a full topic covered on this platform. After writing the F equation of sulfuric acid, you also write the F equation of titanium being oxidized to titanium 4 oxide. So you shall put this side water so that you get titanium. If it's oxidized, you're going to get titanium 3 sulfate. Let me first rub off here. So writing the F equation for titanium, you just, since it's titanium 3 sulfate or it's titanium 4 sulfate, you put the equation, or the equation is the titanium 3 sulfate is in terms of aqueous. So since it's aqueous, we make sure that the F equation for titanium is also in terms of aqueous. So it's going to be a titanium solid getting transited to titanium 3 ions. Now you are going to change this. The acid oxidizes it to titanium 3 sulfate, not 4 sulfate. It's titanium 3 sulfate, and the acid is going to be reduced to sulfur dioxide plus water. Now we balance these two equations and we combine them by eliminating electrons, as we discussed this further in redox reactions. Now after balancing using electrons, you are going to get the same balanced equation as the one I listed here. And the reason why I emphasize that is because majority of you do not know how to balance equations involving redox reactions. So make sure that you make it a practice under balancing equations that are involving redox reactions, especially with hot concentrated sulfuric acid, because it's an oxidizing element together with other reducing elements or compounds, and you understand how to balance such equations. Now, after covering the reactions that are involved by titanium, you are going to transit to the compounds that are going to be formed by titanium. Now, for transition elements, we say that one of the characteristics of transition elements is that they form variable oxidation states. And you are going to see that titanium is going to form compounds in the +3 and then the +4 oxidation states, because that are the most stable oxidation states. And you are going to look at, in the previous video, you looked at how these oxidation states are formed by the respective elements. And you're going to emphasize it the more by saying that in the +3 oxidation state, titanium still has 1 electron in the 3d orbital. And hence titanium 3 compounds are going to be colored and paramagnetic. Remember that we told you for something to be colored or paramagnetic is that we must have unpaired electrons in the 3d orbitals. So since titanium 3 compound has an electron in the 3d orbital, which is an unpaired electron, it qualifies to form colored compounds together with paramagnetic compounds. And we are going to say that in the +4 oxidation state, titanium has lost all the electrons in the 3d orbitals, and therefore titanium 4 compounds are neither going to be colored nor paramagnetic, because we say that to fulfill these properties, we must have unpaired electrons in the 3d orbitals. Now, since it has also the electrons in the 3d orbitals or subenergy levels, that means that it does not qualify to form colored compounds or paramagnetic compounds, because it has no unpaired electrons in the 3d subenergy levels. Now let's look at the formation of titanium 4 compounds. Now we are going to look at the formation or chemistry behind titanium 4 chloride. And I'm going to say that this can be prepared by heating. A condition must be there. The condition here is heating titanium in dry chlorine gas. The condition on chlorine is going to be that it's supposed to be dry. So writing the balanced equation, titanium reacts with chlorine to form titanium 4 chloride. Now just to give a review about balancing equations. When you're balancing equations, make sure that you have somewhere to note. When you're balancing equation, we start with metals. You make sure that the metals are properly balanced. And then secondly, you make sure that non-metals are balanced next, which is the second step. Non-metals other than oxygen and hydrogen. After balancing non-metals, after ensuring all non-metals are balanced, you balance oxygen as the second last. Now when you're balancing oxygen as the second last, we make sure that we add water to the side that is lacking enough oxygen atoms. I hope you are quoting these ones well, because this is a key to balancing equations. So the side which lacks enough oxygen atoms, you add a water molecule and you balance the oxygen atoms that must be added. And then lastly, we balance hydrogen last in any equation that you will have. Hydrogen as an atom or an element is balanced last when you're balancing equations. So looking at that concept that I've given you, so if you have to look at this equation, titanium reacting with chlorine, let's say 2 was not there, to form titanium 4 chloride, first of all, you make sure that the metals are balanced. Titanium is 1 this side, also titanium is 1 this side. But chlorine, we have 2 atoms this side, and this side we had 4. Because chlorine is the non-metal, and he said that the non-metal is the second to be balanced. So that's why I put here 2. And that's equation balancing has been simplified. You make sure that you practice what I've told you in details to see it happen in real time, because you need speed to solve inorganic chemistry numbers in papers, especially paper 2 chemistry. Now looking at titanium 4 chloride, another properties it has is that it is a colorless swimming liquid that is readily hydrolyzed in water. Now let's go back to why it's colorless. Here transition elements form colored compounds. We have already stated that here titanium in the plus oxidation state, it has no electron in the 3d orbitals, and that means that all the electrons, it has no unpaired electrons which qualify for transition elements to be colored or paramagnetic. So you're going to say that it is a colorless swimming liquid that is readily hydrolyzed in water. Readily hydrolyzed in water, it means that it reacts with water to form respective oxides. Just like we looked at chlorides of group 4, also titanium is a simple liquid. So titanium tetrachloride, or a volatile liquid, titanium tetrachloride, which is a liquid reacting with water, it forms titanium oxide together with hydrogen chloride gas. And remember that these reactions are similar to those in group 4 elements, just like we uploaded a video about it also in this platform. So titanium chloride reacts with water to form titanium oxide and hydrogen chloride gas. Now assuming that the balancing components, because it's the main reason why majority of you ignore chemistry or inorganic chemistry. So let's look at the balancing reason basing on the terms that I discussed earlier on here. So we said that we balance metals first. Titanium is 1 this side, titanium is 1 this side. And then we say that we balance non-metals next, apart from oxygen and hydrogen. So chlorine, we're having 4 atoms of chlorine this side, and this side we had 1. So that's why we placed here 4 to make sure that the atoms of chlorine are well balanced. After balancing non-metals other than oxygen and hydrogen, the second last to be balanced is always oxygen. So we ensure that oxygen is balanced on either sides. So if you look at this side, we only had 1 oxygen atom on water molecule, and this side we only had 2 water molecules on the titanium oxide. So to balance up oxygen, that's why we had to put here 2. And therefore oxygen is balanced. So we balance hydrogen lastly. If you look this side, hydrogen is 4, and if you look this side, also hydrogen is 4 atoms, and thus your equation is properly balanced. So you have to make sure that you practice all those concepts that I've talked about in details. for you to make equation balancing as easy as possible. Now looking at another element, you're going to be looking at vanadium, and you're going to start with the reactions that are involved by vanadium. So you're going to start with the reaction with chlorine. Just like titanium, also conditions must be involved before writing an equation. So we shall say that heated vanadium reacts with chlorine or dry chlorine to form vanadium chloride, which is a dark red covalent liquid. So vanadium reacting with chlorine to form vanadium chloride. Now use the chemistry of balancing equations to try and balance this out without these two. So another reaction is going to be the reaction with air, and we're going to say that heated vanadium reacts with air to form vanadium 5 oxide, which is an orange solid. So vanadium reacts with oxygen to form vanadium oxide. Now let's look at the balancing of this equation. Let's look at the balancing of this equation from scratch. So if at all vanadium is reacting with oxygen gas to give us vanadium 5 oxide, first of all, we must make sure that metals are balanced. So if you look here, this side on the left-hand side, we have only one vanadium atom because it's a metal. And this side, we only have 2 vanadium atoms. So that means that we shall put here 2 initially. And if you look at that means that vanadium is balanced on either sides. That means that we are going to balance oxygen next. This side we are having 5 oxygen atoms, and this side we are having 2 oxygen atoms. To make sure that oxygen atoms are balanced, we have to put here 5 over 2. And therefore, our equation is going to be balanced in such a coincidence. But some people hate fractions, so you have to multiply through by 2 over each and everything. So we shall multiply here by 2. When you multiply this by 2, this 2 goes away, and this one becomes 4. So that's how the balancing of vanadium 5 oxide came about, when vanadium is heated in oxygen. Now let's look at the compounds that are involved by vanadium. Now we are going to say that vanadium forms compounds that are present in the +2, +3, +4, and the +5 oxidation states. And we are going to say that the +4 is the most stable oxidation state of vanadium. All the oxidation states of vanadium can be observed in the aqueous species formed when a solution of ammonium vanadate 5 is treated with dilute sulfuric acid together with a zinc metal. Now this is going to be a summary of the various oxidation states that are formed by vanadium, but however, these ones are not crucial while answering your papers because vanadium is mostly examined under chemical criteria where we use it as a catalyst. So this is just to highlight your view about the formation of the various oxidation states provided we have dilute hydrochloric acid together with a zinc metal. So first we react vanadate 5. And the summary of the color changes that are going to be involved is that when you're having vanadate in this oxidation state, it must be, if you catch it for oxidation state in this compound, it's going to be +5. This compound is going to be +4. This compound is going to be +3, and then this compound is going to be +2. And then vanadium in the +5 oxidation states, the compounds that are going to be formed are going to be yellow in color. Vanadium in the +4 oxidation states, the compounds that are going to be formed are going to be blue in color. And then vanadium in the +3 oxidation states, the compounds that are going to be formed are going to be green in color. And vanadium lastly, in the +2 oxidation states, the compounds that are going to be formed are going to be violet in color. Now we are going to be looking at the main transition element of this video, which is going to be chromium, which is the most to be examined by both UNEB together with the mock bodies. Now make sure that you understand this chemistry of chromium properly. I try to summarize it and be direct to the point as far as possible. So make sure that you focus and you understand each and every concept, because I didn't bring anything excess or out of context from what you're supposed to be examined. Under transition elements, manganese, zinc together with chromium are the most elements to be examined due to their chemistry or due to their interesting chemistry or reactions and the variance in oxidation states. So just like others, you're going to be starting with the reactions that are involved by chromium, and you're going to say that if chromium is to react with air, the conditions must be stated. First of all, chromium must be heated. Now I'm underlining these ones because these are the mistakes that majority of you make. You say that chromium reacts with air to form chromium trioxide. Now that's not right, because chromium as an element cannot react without any condition. And that's why I am so emphasizing the conditions that must be presented on each and every condition statement of the equation that you make. So heated chromium reacts with air to form chromium trioxide. So first of all, the equation is going to be like this. Like I said, I like balancing these equations together with you according to the concept of balancing equations that I gave you. So you're going to say chromium reacting with oxygen to give us chromium trioxide. So chromium trioxide is going to be in this form. So we said that we balance metals first. So this side you're having one chlorine atom, and this side you're having two chlorine atoms. That means that we are going to put here 2 so that to ensure that chromium atoms are balanced. If we go to oxygen, this side I'm having 2 oxygen atoms, and this side I'm having 3 oxygen atoms. For us to balance oxygen, I will put here a fraction of 3 divided by 2. So that if I multiply 3 by 2, I'll get 3 oxygen atoms this side, and therefore oxygen atoms are going to be balanced. But usually we hate fractions. Some people hate fractions, but they are marked in UNEB. But some may hate fractions, so I multiply 2 by 2. And this one is going to become 4 as given in the question. This one is going to remain 3, and you're going to have a 2 on our compound that is being formed. And that's how we balance equations. Now let's go at the second part of reaction of chromium together with water. Now we're going to say that with water, heated chromium is going to react with steam so that you can form chromium trioxide together with hydrogen gas. So chromium reacts with steam. Now steam, the state must be a gas, not a liquid. Once you say the common errors in the papers submitted for marking is that students talk about steam and they go on and write liquid here. Now that means that you have changed the statement that you wrote. Instead of writing gaseous state, you write liquid. That means that you are reacting chromium with cold water, and therefore the statement won't carry any mark. So the marks that you'll be carrying are going to be for the equation. So when you're looking at the reactions with water, first of all, conditions must be stated. Chromium must be heated and it must be reacting with steam to form chromium trioxide together with hydrogen gas. So what you do here is that you get chromium reacting with water to form chromium trioxide and hydrogen gas. Now we follow the concepts of balancing equations. We said that we start balancing metal atoms first. Our metal atom here is going to be chromium. On the right hand side, you're having 2 chromium atoms. That means that I'll put here 2 to ensure that I'm having 2 chromium atoms this side. Now we say that the second step is to balance nanometals next, other than oxygen and hydrogen, and we don't have any. So we shall go to the third step of balancing oxygen atoms. So if you look this side, we're having 3 oxygen atoms on chromium trioxide, and this side we're having only 1 on water. So that means that I'll put a 3 on a water molecule to ensure that oxygen atoms are balanced. Now after balancing oxygen, we balance hydrogen last. So we make sure that hydrogen atoms are balanced on either side. So this side, if you look at the left hand side, I'm having 6 hydrogen atoms, and this side I'm having only 2. That means that I'll put here 3 to balance hydrogen atoms, and that's how the balancing of this equation came about. And similar applies to the balancing of other equations. I say that I'm going to be repeating that concept throughout the video because transition chemistry is full of equations, and if you don't know how to write equations and balance them, then you are in danger. So we go to part C with chlorine, and when you're looking at chlorine, heated chromium reacts with dry chlorine gas to form chromium trichloride. Now chromium reacts with chlorine to form chromium trichloride. What you need to know is the product that is being formed, and then you need to deal with the balancing according to the concepts that I told you. So here, if I told you I was know these coefficients, chromium was one on the left hand side, it was also one on the right hand side. But on the left hand side, you had 2 chlorine atoms, and this side we had 3. So to balance this up, we had to write 3/2 against chlorine gas. But for us to eliminate electron to fractions, we multiply through by 2. That's why you are seeing here that's why you saw here 2 and here 2 on our product, and we're having here 3 on our chlorine gas. So it's as simple as that. Balancing equations is very vital in inorganic chemistry. I need to be very comfortable at writing them and balancing them as quickly as possible. Now, reaction number 4 is going to be reactions that are involving alkalis. So with this, we are going to say that chromium reacts with condition is going to be that chromium, now here chromium must not be heated. Whenever you're reacting an element with an aqueous compound, we don't heat it, and that's the main other error presented by students. Chromium must not be heated. So what we say that chromium reacts with hot concentrated sodium hydroxide solution, forming a green solution of sodium chromate 3 and hydrogen gas. Now here, giving an observation may not be vital. What is needed in the statement are the conditions together with the product being formed. So another student can say, chromium reacts with hot concentrated sodium hydroxide solution, forming sodium chromate 3 together with hydrogen gas. And giving an account for that is that we're going to write our chromium reacting with sodium hydroxide to give us the chromate. Now we're having 2 forms, but the majority is this one. You can either write your complex in this form, or you can write your complex in this form. So let me explain my balancing of equations that are involving alkalis in this format. Now initially, we are going to take an assumption that these 2, or the coefficients that are involved on balancing our equations, are not present. So initially, we are going to talk about balancing equations that involve alkali step by step. So whenever you're reacting any element or a compound with an alkali, we look at the following criteria under balancing equations. So number 1 is going to be make sure that you balance the charges first. So charges on the left hand side must be equal to the charges on the right hand side. And on the left hand side, we balance charges using the hydroxide ion. On the right hand side, we balance charges using the complex that is being formed. So you need to take note of that first. Secondly, we start following the steps that we were following initially in balancing equations. You balance the metal atom first. After balancing the metal atom first, you go to the balancing of the non-metal next. After balancing non-metal next, you go to the balancing of the oxygen atom second lastly, and then later you go to the balancing of the hydrogen atom as last. Now here there are some modifications that are going to be involved when handling the last 2 steps. When a side lacks sufficient oxygen atoms, we balance that side using water molecules, for as long as you are dealing with an equation involving reaction of a compound or an element with an alkali. Now the side that is going to be lacking enough hydrogen atoms, we are going to be adding hydrogen gas to balance up the hydrogen atoms on that side. Now I hope you have taken down all the notes about balancing equations that involve alkalis. Now let's go into details of how this equation came about. So first of all, we start with balancing charges. So if you look at the charges, let me first change the ink. If you look at the charges this side, they are well balanced to the charges this side, because I'm having -1 here. I'm also having -1 on the hydroxide ion. Now the purpose of the hydroxide ion is to balance charges, so we are done balancing charges. Now we go to the metal atom. I'm having 1 chlorine atom. I'm also having 1 chlorine atom this side, so it means that chlorine atoms are balanced. Now lastly, we go to the non-metal, or second lastly. But the non-metal is absent. We have oxygen next, so we are going to go to oxygen. If you look at oxygen, this side I'm having 1 oxygen atom, and this side I'm having 4 oxygen atoms. So what you do is that this side is lacking enough oxygen atoms, and we say that the side which is lacking enough oxygen atoms, we add there a water molecule to balance up the oxygen atoms. So if I'm adding water to get 4 oxygen atoms on my left hand side, I need to put here 3. So that 1 plus these 3 here is going to balance up the oxygen atoms. And since oxygen atoms are balanced on either sides, I go to balancing of hydrogen atoms. So if you look this side, I'm having only 4 hydrogen atoms. And if you look this side, I'm having, this is 6 plus 1, I'm having 7. So that means that this side, or the right hand side, is one which is lacking enough hydrogen atoms. And we say that the side which is lacking enough hydrogen atoms is where we add the hydrogen gas. And then we make sure that we balance up the hydrogen atoms using this hydrogen gas that we have added. So I need to 7 this side, and I'm already having 4. That means that I'll multiply this hydrogen by 3 divided by 2. I hope you understand. 3 divided by 2, I'm going to have 3 hydrogen atoms as a whole here. So 3 plus 4 hydrogen atoms are going to be balanced. Now you can either leave your equation here, or you can make it the way I presented this one, by simply multiplying through by 2. When you multiply through by 2, on the hydrogen you are going to remain with 3, and you are going to have here 2. When you multiply this one by 2, you are going to have a 6 here. And when you multiply the hydroxide by 2, you are going to have a 2 here, and you are going to have a 2 on chromium. Now take note that this equation is the same as the equation for aluminium. Chromium has the same chemistry like aluminium in the +3 oxidation state. And that's how the equation came about. I hope everyone understood rating or balancing equations that involve alkali. And if you did so, you put a like on this video so that I understand whether you are understanding what I'm teaching, or there are some improvements that need to be made. So we go to part E, or the number 5, which is going to be the reaction involving hydrogen chloride gas. So the conditions first in the statement. So we're going to say that heated chromium reacts with dry hydrogen chloride gas to form chromium 3 chloride. And with that, you're going to have your chromium. Let's ensure that, let's first remove the coefficients involved in balancing. So chromium reacts with hydrogen chloride gas to give us chromium 2 chloride. Now this reaction is very common, and it's the only reaction by which we can prepare chromium 2 chloride. And this reaction is similar also to iron. Compounds that are having more than one oxidation state, for us to form a chloride of the least oxidation states, we make sure that we use dry hydrogen chloride gas, and we heat it with that specific element. So when chromium is heated with dry hydrogen chloride gas, we form a compound in the lowest oxidation state, which is chromium 2 chloride. But if we react it with chlorine directly, remember that chlorine is an oxidizing gas, so it's going to form the most stable oxidation state, which is chromium 3 chloride. So this is the only way we can form chromium 2 chloride. So understand that and put a scientific note on this one. So chromium reacts with hydrogen chloride gas to give us chromium 2 chloride. So that's what, assuming that's what you know. So balancing this up, we shall 1 chlorine atom this side, 1 chlorine atom this side. We go to non-metals. Non-metals, we're having chlorine. We're having 1 chlorine atom this side, and we're having 2 chlorine atoms this side. So we shall put here a 2 on hydrogen chloride. Now to balance up hydrogen atoms, assuming that you didn't know that hydrogen is given off, here you're having 2 hydrogen atoms, and this side you don't have any hydrogen atom. For us to balance hydrogen, on the side which is lacking hydrogen atoms, we add their hydrogen gas molecule. And that's how you balance equations. I say that make sure that if you have understood this, you like this video. I understand whether you are getting the information or you are not. And you put a comment about the progress that you are having and the issues that you are having about equation balancing. Because under transition chemistry, we are going to have numerous equations. And my duty here is to make sure that I simplify them to the minimum. So make sure that you are not only watching the video for the sake of taking notes, but also for the sake of understanding. So we go to the CK3 reaction, and we're going to say that reaction with acids, and we're going to say that chromium reacts with warm dilute sulfuric acid together with hydrochloric acid to give the corresponding chromium 2 salts and hydrogen gas. Now it's giving the chromium 2 salts and hydrogen gas because these acids, dilute sulfuric acid together with dilute hydrochloric acid or concentrated hydrochloric acid, do not have oxidizing powers. So any acid that does not have oxidizing powers always gives us the least possible or least stable oxidation state of chromium, which is +2. So chromium reacting with either of the dilute sulfuric acid or hydrochloric acid, we get chromium 2 salts together with hydrogen gas. And if you look at the balancing of this equation, it's going to be balanced. Chromium is 1, chromium is 1. Hydrogen is 2, you have to put here 2 to ensure that the atoms are properly balanced. Now proceeding, we are going to say that chromium is oxidized by hot concentrated sulfuric acid to chromium 3 sulfate, and the acid is going to be reduced to sulfur dioxide and water. So the equation is going to be this. Now I told you that this, whenever you see a concentrated acid oxidizing and it gets reduced to sulfur dioxide and water, this is a redox reaction. You have to make half equations for sulfuric acid, which is going to be sulfate ion plus hydrogen atoms plus electrons to give you sulfur dioxide and water. You balance that equation first, and then you also write the half equation of chromium being oxidized to chromium 3 sulfate, and that's going to be simply chromium as a solid getting oxidized to chromium 3 ions. To balance up this, you need to add 3 electrons. Then after that, you add these two half equations by eliminating electrons using the redox chemistry knowledge. By eliminating electrons, you add the two equations and you are going to get the same balancing like this one. But what's going to vary is that you are going to get an ionic equation. But if you can get an ionic equation, it is also marked. If at all you can convert this ionic equation into this format, you are also going to get equal marks. So both equations are going to be marked. Students who use ionic equations and who use these ones who use atomic equations are going to be marked because everything carries a mark. But the ones to easily balance up these equations and to avoid cramming, you have reactions that involve redox reactions, you must make half equations as a side work. And you understand how they come about. Majority of your students is that you cram these coefficients, which is an ineffective strategy, and you easily forget how to balance those equations after some period of time because you focused at cramming. So you're going to say that chromium is rendered passive by hot concentrated nitric acid, just like chromium. So chromium and most of the transition elements that have positive 3 as their stable oxidation state do not react with nitric acid, and majority of the transition elements render concentrated nitric acid passive. So let's look at the compounds of chromium. Now chromium forms compounds in the +2, the +3, and the +6 oxidation states. Now the +3 oxidation state is the most stable out of all the states. Now let's look at how chromium 2 compounds are formed. Now I'm going to say that compounds of chromium in these oxidation states are going to be very unstable, and then they are going to be strong reducing agents. If something is very unstable, that means that it requires to go to its stable oxidation state. So chromium 2 compounds readily oxidize in air to form chromium 3 compounds. Now you're going to say that oxidizing agents like chlorine can oxidize chromium 2 to chromium 3 chloride. That's why when we heat chromium, I say that for us to get chromium 2 chloride, we have to heat chromium together with hydrogen chloride gas. It's a very common question. But when you heat chromium directly with chlorine, you're going to get chromium 3 chloride because chromium has its stable oxidation state as +3 and chlorine is an oxidizing gas, but hydrogen chloride is not an oxidizing gas. So that's why when you react chromium with hydrogen chloride, we form chromium 2 chloride. But when you react chromium with chlorine gas, you form chromium 3 chloride. So you have to take note of that. So if you're having a solution containing chromium 2 ions and then you bubble it with chlorine gas, you're going to form chromium 3 ion together with chloride ions because chlorine is going to be reduced to chloride ions. Now the second compound of chromium 2 salt is going to be the chromium 2 chloride, and you're going to say that this is a white solid that is prepared, as we already said, heating chromium metal in dry hydrogen chloride gas. Conditions in this statement are chromium must be heated in the condition on hydrogen chloride gas is that it must be dry. So you make sure that you have those statements whenever you are presenting such an equation. So chromium is heated with hydrogen chloride gas from chromium to chloride and hydrogen, and I've already discussed in details how the balancing of this equation came about. And it's your duty to practice them one by one until you get good at it. So looking at chromium 2 hydroxide, we are going to say that this is a yellow solid which precipitates when a little alkali is added to a solution of chromium 2 salt. So chromium 2 ion reacts with hydroxide ion to form chromium 2 hydroxide. But this happens when you add just a little alkali to chromium 2 salt. Now let's look at the formation of the chromium 3 compounds, which are going to be compounds of chromium in the +3 oxidation state, which is the most stable oxidation state of chromium. Now we are going to say that chromium, we are going to start with chromium 3 hydroxide, and we see how it is formed. Now chromium 3 oxide is a green ionic and amphoteric solid that can be obtained by heating chromium 3 hydroxide or ammonium dichromate. Now mock bodies like to present this one. I've told you that this one is the most examinable in mock bodies, and this one may be relevantly presented in UNEB or your practicals. So when in your practicals, you may form a green solid or a green precipitate, and you may be prompted to heat it and watch the observation. So what they want you to observe is going to be this reaction. So when you're heating an hydroxide, we form chromium 3 oxide together with water. But let's see how that equation can be balanced. We say that we start by balancing metals. If you're having 2 chlorine atoms this side, you have to put here 2 so that chlorine atoms are balanced. After balancing chlorine atoms, you balance oxygen atoms. So this side you're going to have six oxygen atoms, and this side you're having 3. Now remember that we had just put water, this 3 was not there. So for us to balance this water, we had to put here these 3, which you are seeing. And therefore oxygen atoms will be balanced. Looking at hydrogen, this side you're having 6 and this side you're going to be having 6. So equation balancing with that becomes as easy as required. I hope everyone has understood that concept. So if you're heating ammonium dichromate, you also form chromium 3 hydroxide, nitrogen gas together with water. And the balancing is going to follow the same criteria. First of all, ensure that metal atoms are balanced. The metal here we have is chromium. So chromium 2, we're also having chromium 2. For as long as you know the products that are being formed. Next, you balance the non-metal. Non-metal you're having here is nitrogen. Nitrogen, you're having 2 atoms this side and you're having 2 atoms this side. Next atom is going to be oxygen, and we balance oxygen using the water molecule. So if at all you know that you're having oxygen to be 3 here and you're having 7 oxygen atoms on your left hand side, that means that on water you put here 4 to ensure that oxygen atoms are balanced. When you're having water on one side, you balance always balance oxygen atoms using the water molecule, just like we looked at that under reactions that involve alkalis. So after balancing the oxygen atoms, we look at hydrogen, and hydrogen you're having here 8, and hydrogen you're having here 8, and the equation qualifies to be balanced. So the key takeaway here is that balance metals first, balance non-metals, which is nitrogen, balance oxygen as the second last, and then lastly, you balance hydrogen. And as simple as that. Now looking at the reaction with acids to form corresponding chromium 3 salts. Chromium oxide reacts with acids forming chromium 3 salts together with water, as any other oxide does, or amphoteric or basic oxide does. When they are reacting with alkalis, we form chromate 6 salts. And I've told you about the balancing of this equation that involve alkalis. We follow the same steps. So initially, let's take a review about the balancing. So let's take, because the other time we looked at an element and this time it's a compound, but we follow the same steps. Nothing is going to change. So first we make sure that charges are balanced. That's the first step when you're dealing with alkalis. So -1 here, -1 here. And then the other step, we balance metal atoms. So chromium is 1 this side and chromium is 2 this side. So we had to put here 2 to ensure that chromium atoms are balanced. But you have to take note of the first step. When you put here 2, the first step is going to be violated. That means that charges here are going to become -2, because if you multiply this 2 by this negative above here, you get -2. And therefore, with balanced charges, we say that we balance charges on the left-hand side using the hydroxide ion. So that's why we placed here a 2 opposite the hydroxide ion. So that means that charges are going to be balanced again, together with the metal atoms are going to be balanced again. That's the first step. Now the second step, we go to balancing oxygen. So oxygen, we're having 3 plus 2 is going to be 5. Remember that initially this water was not there. We only know that chromium oxide reacting with hydroxide to give us a complex. That's what we know. We don't know where to add water, because I told you the side that lacks enough oxygen atoms, you add water molecule. And the side that lacks enough hydrogen atoms, you add the hydrogen gas molecule, and you balance that side. So looking at oxygen atoms this side, we had 5 initially, and looking at this side, we had 8, if you look properly. So that means that this side, we lacked 3 oxygen atoms. Now to balance 3 oxygen atoms, we had to introduce this water molecule here. Together with the 3, and we attach a 3 on it so that we can balance the oxygen atoms. Now after ensuring that you have balanced oxygen atoms, you go to balancing the hydrogen atoms. If you look this side, this is going to be 2 plus 6 to give you 8. And if you look at the right hand side, also hydrogen atoms are going to be 8 in number. And that means that your equation is balanced. Now you follow the same concept. Like I told you, the compounds of chromium and alkalis are going to be the same as for aluminium. That means that also aluminium oxide is going to have the same balancing coefficients, because they are all in the same oxidation states. So you can also compare this method and see how you can balance up that equation according to the chemistry we have discussed. Now let's look at the second component that is going to be involving chromium 3 hydroxide. Now chromium 3 hydroxide, most of the compounds of chromium in the +3 oxidation state are going to be green in color. So chromium 3 hydroxide is a green amphoteric solid that is formed by precipitation when an alkali is added to a solution of chromium 3 salt. But we make sure that this alkali is being added in less amounts, because when you add it in excess amounts, since it's amphoteric, it's going to form a complex. So chromium reacts with little alkali to form chromium 3 hydroxide, which is a green precipitate, as you look at that in your practicals. And you also say that it reacts with dilute acids to form chromium 3 salts. When you're having chromium 3 hydroxide reacting with a dilute acid, we form chromium 3 salts together with water, just like the basic science of reactions of bases and acids. We form a salt and water. So you're also going to say that it reacts with alkalis to form chromate 3 salts. So chromium hydroxide reacting with alkali, we form this complex as we have looked at it. This is going to be an excess alkali, or we can present it in this form. Now let's look at the chromium 3 salts and their properties. Now you're going to say that these are generally prepared by reacting chromium oxide or hydroxide together with these acids. And then the solutions of chromium 3 salts are going to be acidic in nature. This is a very important statement. Solutions of chromium 3 salts are going to be acidic in nature. Now this one is going to come under salt hydrolysis, and we looked at salt hydrolysis under the ionic chemistry videos that I uploaded on this channel in the physical chemistry playlist. So there is a topic of salt hydrolysis, and I explained this topic in details because it's a very examinable topic, both paper 1 and paper 2. And since majority of students are not understanding it, it's coming back each and every year. So make sure that you are very good at salt hydrolysis, and you understand why we say that chromium 3 salts or elements with a positive 3 oxidation state are going to have their solutions existing as acidic. You need to understand that. It's under the videos of ionic equilibria under salt hydrolysis in the physical chemistry playlist. So I'm going to say that this is because of hydrolysis of the hydrated chromium 3 cation. But we looked at this explanation more in details. This is just to highlight what we already covered. So I'm going to say that chromium 3 cation has a very high charge density, thus becomes very hydrated in solution. The coordinating water molecules are polarized, weakening the oxygen to hydrogen bond so that the proton can easily be lost to the solution, making it acidic. I say that this is a general review or a summary of what salt hydrolysis is, but if you want to go deep into it, which I emphasize, after this video, you must make sure that you understand that video that I posted about salt hydrolysis. It's under unique equilibria, under the physical equilibria playlist. So make sure that you visit it and you understand it properly. So you write your hydrated chromium 3 ion undergoing hydrolysis to give us protons in solution. Now the protons that it gives off are the ones that are responsible to make our solution acidic. Now notice that this equation involves a series of steps until we get a green solid of the hydrated hydroxide. This is just the initial step of the equation, and it's not marked. This was just to highlight how protons are going to be released in solution. But this step undergoes like a series of 4 to 6 steps until we form a hydrated chromium 3 hydroxide, which is a solid green in color, plus loss of 3 protons. Now, some cases, when you're having here water on this side, instead of protons, we form hydroxonium ions, just like I well elaborated it under that video that I've referred you to under salt hydrolysis. So you make sure that you visit it out and you understand hydrolysis of the chromium 3 salts together with aluminium. Now let's look at the chromium 6 compounds. Now we're going to look at the chromium 6 oxide, which is written as CrO3, and let's look at how the chromium 3 or chromium 6 compound is formed. Now first we are going to say that chromium 6 oxide is a dark red that can be prepared by simply adding concentrated sulfuric acid to a saturated solution of potassium dichromate. Now if you're having potassium dichromate and then you add concentrated sulfuric acid, we form what we call chromium 6 oxide together with the water molecule. The balancing of this equation is going to follow the same appropriate steps like I told you before. Now when heated, it decomposes to give us chromium 3 oxide and oxygen gas. So when you heat chromium 6 oxide, we are going to form a compound which is in the most stable oxidation state, which is the chromium 3 oxide, together with evolution of oxygen gas. The balancing of this equation is going to follow the same criteria like we looked at before. So if at all it's an acidic oxide that dissolves in water, chromium 6 oxide is an acidic oxide. Now you have to take note of this. Chromium 3, the chromium in the an oxide of chromium in the plus 3 oxidation state is amphoteric in nature, but an oxide of chromium in the plus 6 oxidation state is an acidic oxide. Now this has been used by the mock bodies to trick majority of the students. They tell you they describe an oxide of chromium which is acidic and they don't specify it. So as a student, you must know which oxide of chromium is acidic, which one is basic, and which one is amphoteric. The one in the plus 3 oxidation state is amphoteric. The one in the plus 6 oxidation state is acidic, and the one in the plus 7 oxidation state is basic. You have to understand that properly, and that's why I made these notes as brief as possible for you to digest each and everything that was presented here. So if at all you get the chromium 6 oxide, which is an acidic oxide, which you must underline as you're taking your notes. It is an acidic oxide that dissolves in water to form chromic 6 acid. So chromium 6 oxide reacts with water, forming chromic 6 oxide. Balancing this equation is going to be based on the principles that I told you. Chromium is 1, chromium is 1. You go to oxygen. Oxygen is 4, oxygen is 4. And then you go to hydrogen lastly. Hydrogen is 2, hydrogen is 2. So that means that this equation is well balanced. Now looking at another component, you are going to say that chromium 6 oxide reacts with alkalis, forming the chromate 6, which is the chromate 6 ion. You may remove this S and you just say chromate 6 ion. So when you react chromium 6 oxide together with an alkali, we form what we call the chromate 6 ion, which is written in this form, together with evolution of water. And if you try to balance out this equation, we say that equations that involve alkalis, you balance the charges first. So if you look here, the charges here was -2 on the right hand side. So that's why we placed here 2 opposite the hydroxide ion, because we said on the left hand side, we balance charges using the hydroxide ion. After balancing charges, you go to the metal atoms. So chromium was 1 this side, chromium was 1 this side. After that, you balance oxygen atoms. If you look at oxygen on the left-hand side, we're having 4. And on the right-hand side, together, if you look at on the left-hand side, you're having 5. And on the right-hand side, we also have 5. If you look at hydrogen atoms lastly, we're having 2 on the right-hand side and we're having 2 on the left-hand side. So that means that the equation was properly balanced. Now here we are going to be looking at the chromate 6 compounds or the chromate 6 ions or salts. Now we are going to say that chromate 6 are salts that are derived from the chromic 6 acid, which is so that we get it by reacting chromic 6 oxide, which is an acidic oxide, with water to form chromic acid or chromic 6 acid. Now we are going to say that they are going to be generally insoluble in water except sodium, potassium, and ammonium chromates. And then the insoluble chromates can be prepared by precipitation reactions, and therefore we are going to look at the qualitative chemistry of chromium leading to formation of all this. And we use all these salts under a topic of solubility product under ionic equilibrium, which is also a full topic which was discussed on this channel. So barium reacts with chromate to form barium chromate 6. The same applies to lead, forming lead chromate. The same applies to silver, forming silver chromate 6 solid. They are all precipitates. So you're going to say that all the above chromates are yellow except the silver chromate, which is a dark red solid. So majority of the observations that we get in the laboratory when you use any reagent containing the chromate ions and you are confirming barium or lead, we have to get yellow solids because it's a very common reagent in the laboratory. So what you're going to say is that the chromate ions has a tetrahedral structure. Now I didn't draw it here because I've just uploaded a video about drawing structures. Drawing these structures under structure and bonding, and it's a very elaborative heading about that video that you are drawing structures. Now those videos are 3. One of them is introducing the topic about polarity. The other one is teaching you how to draw those structures. And the other one is teaching you how to explain those structures. They are all must be followed appropriately. Now going to the third part, chromates are only stable in alkaline medium. In acidic medium, they convert to dichromates. Now the stability of these oxidation states is very important. You have to understand that the chromate 6 ion is only stable in alkaline medium, and you should underline that because the things that I'm emphasizing, they are mostly examined in mock bodies. And the UNEB examination board does not emphasize them most because it tends to favor majority of the students. But the mock bodies, we try to ensure that you as a student, you have all the information that is required when we set a specific topic or subtopic. So if you are to set chromium, we have to highlight all the main key areas that are involved in chromium, and that was the purpose of this presentation or the notes that I'm giving to you to equip you with enough details about what you're supposed to put in your examination. So if at all the chromate 6 ion is stable in the alkaline medium, that means that if we put it in another medium, like the acidic medium, it's going to convert to a medium which is stable under the acidic medium, and that is going to be the dichromate, which is commonly used in organic chemistry as a reducing or an oxidizing agent. So having chromate 6 ion placed in an acidic medium, it transits to a more stable oxidation state, which is going to be the dichromate ion, and also forming water. Balancing is done in the same way. Chromium first, oxygen next, and then you balance hydrogen lastly, and you're going to end up with this equation. So I hope you have no issues on that matter. Now let's also look at the chemistry that's involved by dichromates or dichromate 6. Now I'm going to say that these are going to be orange colored salts containing the dichromate ion, which is going to be written in this form as you write it in organic chemistry. Dichromate is written like this. Chromate 6 does not have a 2 or does not have a 2 here, and it has a 4 oxygen atoms. and a negative charge. So you're going to say that dichromates can be obtained by adding the sulfuric acid to a solution of chromate, because we say that chromates are stable under the alkaline medium. So if you put them in an acidic medium, they try to isomerize to the dichromates, giving off water. Now this water is as a result of balancing. So make sure that you balance these equations according to the concepts that I've given you. The main emphasis of this video was to emphasize equation balancing. The other emphasis was to present notes that are in direct approach to answering your questions. And the other concept or the other emphasis was to re-emphasize the presentation of your work when you're approaching chemistry questions, so that you can get the distinction that you want in chemistry. So dichromates are only stable in acidic medium, and in alkaline medium they convert to chromates. Just like we have said that chromates are stable in alkaline medium, when you put them in acidic medium they convert to dichromates. Also dichromates, if you put, they're only stable in acidic medium, so if you put them in alkaline medium, they are going to transit to an oxidation state which is stable in the alkaline medium, which is the chromate 6. So if you put a dichromate in an alkaline medium, it's going to isomerize or transit to a chromate 6 ion, because it's the chromate 6 ion which is stable in this medium. And also, the chromate 6 isomerizes to the dichromate because it's the dichromate that is stable in the acidic medium. You have to be very keen at understanding that, because it's highly examinable. And you need to equip yourself with questions as many as possible. So looking at this, we're going to say that dichromate 6 ions are strong oxidizing agents in acidic medium. That's why when you're writing dichromate 6 in organic chemistry, you stroke it with an acidic medium, because, and we looked at it more in details under the redox reaction topic, which was uploaded in this channel, because they are very good, strong oxidizing agents. So when reacted with reducing species, they cause magnitude, or they cause a variety of observations that we are interested in your practicals in chemistry, because it's a very common reagent that is used in chemistry, especially under organic chemistry practicals. So dichromate 6 in acidic medium transits to give us chromium 3 ions together with water. Now we're going to say that, however, they are not strong enough to oxidize the chlorides to chlorine. Therefore, they can be used in the presence of hydrochloric acid in volumetric analysis. And reactions of dichromates are going to include the following. So let's go over the 6 reactions of dichromates that are involved in volumetric analysis. Now the first reaction, you're going to look at oxidation of the chromium 2 ion to the chromium 3 ion. So you're going to look at chromium dichromate in acidic medium reacting as an oxidizing agent. Now remember that these are all redox reactions, and I'm not repeating explanation of redox reactions because I talked about them. So the first half equation is going to be for this one, in protons, to give you the chromate and water. The other equation is going to be for ion transiting to ion. You balance the two equations using electrons, and then you combine them using the knowledge of redox reactions. Now if you didn't understand redox reactions, you have to either comment about the issues that you are facing. I see how to reframe them. But all these ones are redox reactions, and for you to master these equations properly, you have to understand the knowledge of redox reactions. So the first half equation is going to be dichromate in acidic medium to give you chromate 3 ion and water, and then you balance that up. The other equation, or the second half equation, is going to be ion transiting to ion 3 ions. To ion 3 ion, and then you put electrons, you balance the two half equations. We combine the two half equations using electrons. After that, you add the two equations, and you are going to end up with this equation. It's not complicated. It's only complicated when you try to master it the way it is, which is very impossible. For some of it's possible because you like cramming, but that's not the way we get good at chemistry. So make sure that you put in the work. master redox reactions first, because all these reactions we are going to be looking at are redox reactions. So the observation that's going to be there, whenever you're dealing with a redox reaction, part A, when you're examining these questions, part A, we are going to ask you for what is observed. Now, when you're giving us your observation, make sure that you don't write any name anywhere. Observations must be about color changes. Don't mention any name of a compound, or don't carry out any test of a product that is being formed. Just give the observations that are formed. If it's a colorless gas, say effervescence of a colorless gas. If it's change in color, talk about the change in color only, because that's what you are seeing. It's the purpose of the observation. Don't give or mention names under that. So the observation there is going to be the orange solution turning to green. Orange solution is going to turn to green because their chromate is orange in nature. And when we form chromium 3 ions, the chromium 3 salts are green in nature. So that's why we say that orange solution turns to green. Then the other reaction is going to be oxidation of iodide ions to iodine. And we looked at this also under redox reactions. So I'm going to say that iodide ions are oxidized by acidified dichromate to give us the iodine chromium 3 ions together with water. Now if you look here, the observation is going to be as follows. The colorless solution, which is going to be of potassium iodide, turns brown. Now we are saying that the color solution turns brown because when you're carrying out this experiment, we add acidified dichromate to a solution of potassium iodide. So that means that the observation that we must give must be of the observation of potassium iodide, not the observation of what we are adding. I hope that is very clear. We are adding acidified dichromate to the potassium iodide solution. And therefore, the observation that we make must be strictly for potassium iodide. So we say that the iodide ion, the color solution of potassium iodide turns to brown. Now part C, we shall say that oxidation of hydrogen sulfide to sulfur. And we're going to say that sulfur reacts with acidified dichromate to give us the sulfur solid. It's going to be oxidized to the sulfur solid. Then the dichromate, acidified dichromate, after oxidizing, it gets reduced to chromium 3 ions and water. And I've told you all these are redox reactions. Ensure that you review that topic and you understand how each of these equations were balanced. And you let me know in case you're having any errors in the comment section. I'll be making a video about your issue. Going to the observation here we talk about is going to be for the dichromate, because in this case it's going to be adding of hydrogen sulfide, overpouring hydrogen sulfide in acidified dichromate. So we're going to say that orange solution turns green, and also a yellow precipitate is going to be formed. Now notice that here we do not want in chemistry anything or any word concerning deposit. We do not have deposits in chemistry. Deposits are for mobile monies and other transactions that are being made online or via cash or bank. But in coming to chemistry, we deal with, you either call it a precipitate or you call it a solid. A yellow solid is formed or a yellow precipitate is formed strictly to avoid losing of marks. Now the other redox reaction you're going to look at is acidified dichromate oxidizes the sulfur dioxide gas to form the sulfate ions, and after oxidizing it gets reduced to chromium 3 together with water. So the observation that you're going to keep is going to be that of chromium, because you are bubbling this gas into this reagent. So you're going to say that the orange solution turns green. Now the next concept is going to be oxidation of sulfides to sulfates, and you're going to say that sulfides react with acidified dichromate to give us sulfates, chromium 3 ions, and water. Also here, observation is going to remain the same. Orange solution turning to green, and I've told you that you must make a practice about balancing these equations as a must. Roman number 5, we are going to look at the oxidation of tin 2 to tin 4. Acidified dichromate oxidizes tin 2 to tin 4 ion, and after oxidizing it gets reduced to chromium 3 ions together with water. And the observation here is going to be that the orange solution is going to turn green. Now let's look at the qualitative chemistry that involve the chromium 3 ions. Or whenever you're having a test solution containing the chromium 3 ions, what are the likely observations according to the notes that you have taken? So one is going to be reaction with sodium carbonate solution. Just to give a general overview, any cation with a positive 3 oxidation state gives effervescence of a colorless gas whenever reacted with this solution. So since we're having chromium, we are going to say that a green solid with bubbles or effervescence of a colorless gas is going to be formed. And the green solid is due to hydrolysis, and bubbles of a colorless gas is due to the protons reacting with the carbonate ions to form a colorless gas. Now this question, if at all it is examined under theory, we give it about 45 marks because it's under salt hydrolysis. Or the simple equation for it can be this one, but also there is that equation that I described about under salt hydrolysis, and I've told you that is a video that must be watched by each of you. So chromium reacts with the carbonate in presence of water to give us a green solid of chromium hydroxide together with carbon dioxide gas. Now reacting it with sodium hydroxide, we are going to have a green precipitate which is soluble in excess to form a green solution. And chromium reacts with hydroxide to form chromium hydroxide, but in excess will form a complex of a chromate ion. Now reacting it with ammonia, we form a green precipitate which is going to be insoluble in excess. And the equation is going to be as follows. So chromium reacts with hydroxide ions from the ammonia solution to give us the green precipitate of chromium hydroxide, but it does not react with excess ammonia because we don't have that complex of amine with chromium to be formed. We shall look at the explanation of that under ionic chemistry and the last video of complex ion formation under solubility equilibria. So number 4, we are going to look at sodium hydroxide and hydrogen peroxide, and we are going to say that observation is going to be a yellow solution on warming. The equation is going to be as follows, and this is also a redox equation. You make sure that you understand how it was balanced using the redox knowledge. If at all you understand the concepts I've been teaching you in balancing equations plus redox reaction, there is no equation that will fail you in chemistry. All the equations of yours will be balanced. So make sure that you put effort in balancing equations, because in organic chemistry becomes very easy if at all you understand equation balancing, which is very easy. So number 5, we look at sodium hydroxide, hydrogen peroxide, butanol together with disulfuric acid. This is a reaction which is commonly done in practicals, and what we see is a blue solution which is going to happen in the organic layer, because this topic is under the physical equilibria concept. So we are going to say that equations are going to be as follows. Chromium reacts with hydroxide ion together with hydrogen peroxide to give us the chromate 6 ion together with water, and then the chromate 6 ion react with excess hydroxide in acidic medium to give us this compound or chromium pentoxide together with water, and this is the blue organic layer, the blue solution that you observe in the organic layer. All this compound is what causes the blue coloration in the organic layer. Now this brings us to the end of this video. You advise share the video to your friends and leave a like on this video in case you have found it helpful. So we are going to be proceeding with the chemistry of other transition elements in the next video. This video has been compiled and revised by Olgembe. For any issues about the concepts that have been revised, you leave your concerns in the comment section. I'll look and see how I can address your issues. Make sure that you like the video, share it to your friends so that you can all benefit as a group. It's better you succeed as a team. Now for people having examinations in your papers, I wish you success in your examinations. See you in the next video.